Good morning, everyone. Hope you all had a lot of fun at the party last night. Thank you all for joining us today. Today, you're going to have a lot more fun learning about analyzing semi-structured data like a boss. I'm Meena Balakrishnan, and with me here today is my friend Stephen McDonald. And we are two of the original 7-member team that conceptualized, designed, and implemented the JSON connector in Tableau. Now, if you have never worked on the JSON connector, I assure you that before you leave this room, JSON connector will be one of your most favorite connectors in Tableau. Now, to share a few things about ourselves before beginning the talk, I am a data geek. I love to code. But when I'm not at my computer coding away, I love to travel the world with my husband and spending a lot of time with my little kitten, Pixel. Now, he does look a little grumpy in these pictures, but trust me, he is a darling.
And I am a former athlete turned full-time nerd. I like to do outdoor activities such as backpacking, as you can see here, rock climbing. And my favorite thing to do is both at the same time, but I'm clearly not doing either in this picture.
Thank you, Stephen. Now, let's take a look at the agenda quickly. Now, we'll first look at data explosion. Now, the amount of data we've been consuming and producing over the past few years has increased rapidly. And in this section, we will look at the different factors that led to this data explosion and look at the challenges that this explosion has posed. Now, data can be sliced and diced in different ways, but one of the most important categorization is the one based on the shape or structure of data. So based on the structure of data, we can classify data as semi-structured and structured. And in this section, we will look at the unique properties of both these classifications with some examples. Now, there are several formats of semi-structured data that are available to us. But of these, JSON is one of the most popularly used format. So we will look at what JSON is all about, why it is so popular, and also share some design principles for designing maintainable JSON schema. Finally, we'll look at analyzing semi-structured data. Now, there are several complexities involved in analyzing semi-structured data owing to their unique schema properties. So in this section, we will look at what these complexities are, and we will walk you through how Tableau enables us to overcome these complexities. Now, historically, every time we needed information, we would run to our neighborhood libraries. Now, information was all in the form of analog papers and books. And libraries were the only places where troves and troves of information was available. I still remember the good old days where we used to actually wait for Saturdays when my dad used to take us to the library so we could spend a few hours there. Now, it was not just consumer data. Even enterprise data was all in analog form. Enterprise data was in the form of ledgers and tally sheets. Now, with the advent of internet, information gradually got digitized. Information which was priorly in the analog form slowly got digitized and got converted into digitized documents in data centers which were stored in large corporations. Now, today, data is everywhere. And if I need something, all I need to do is look at my smartphone. Information is available to me at my fingertips. Data has moved to the cloud and into my homes. And here, you will actually look at two of Steven's cousins who are hooked to their smartphones. Now, I hear that they are really good at Clash Royale. Now, if you have not played that game, we would highly recommend that. Now, the funny thing is that today's generation has always been connected, and they are oblivious to the treasure troves called books that were so dear to us. And it's not just smartphones that are always connected. We have a plethora of devices that consume and produce data. Now, even thermostats apparently are smart. They consume and produce data on a daily basis. Now, it has been estimated that an average 3-member household has about 9 connected devices. Now, given all these technological advancements, imagine the amount of data that we are all producing every day. Now, all these technological advancements have led to several primary needs. The first primary need is the need to scale. Now, it has been estimated that every 18 to 24 months, the amount of information that we store doubles. And because of this, there is an yearly increase of 20 to 40% of storage requirements in all our connected devices. The second need is the need for evolving schema. The shape of data is not going to remain the same. The shape of data today may not be the same tomorrow. Let's consider an example. Let's take Netflix, my favorite streaming service. Maybe they are actually storing information about all these movies with fields such as title cover art, artists, etc. Now, tomorrow, they may want to add one more attribute to this array. Now, to accommodate this addition, the schema of data that Netflix uses should be flexible enough. So there is a clear need for evolving schema. Finally, data needs to be transmitted over the network. Now, it is not a surprise that data needs to be transmitted over network, given that we primarily consume data on connected devices. Now, all these three primary needs have made it clearly important that the choice of data or the structure of data is really important for enterprises and applications. There are two major choices that are available to us, namely semi-structured and structured data. Now, to talk about these semi-structured and structured data and to show us how these three needs are met by semi-structured data, let me invite Stephen back on stage.
Semi-structured data is known by many other names, most notably NoSQL and non-relational. It comes in many different formats and architectures, and we're going to talk about some of those in a minute. But first, in order to contextualize our conversation of semi-structured data, I want to make sure that we all have a unified understanding of what I mean when we say structured data. So the phrase structured data is in reference to tabular data that comes from traditional relational databases. Think about data that comes from MySQL or SQL Server or Postgres. A single entity of data from a structured database is a table. And tables are made up of columns and rows, where each column is a single attribute of the data, and each row is a single record of the data. This is a table that represents Lego sets. You can see that we have two string columns, year and pieces, and two numeric columns and three string columns, T1, T2, and description. The types for each of these don't change from record to record. The set ID column is a unique identifier, which we call a primary key. And it is in order to be able to identify any one single row. The primary key doesn't have to be a numeric field, and it doesn't have to be a single column as it is in this case. A primary key is more precisely described as a non-zero set of columns, which when combined represent a unique value in the data set. But a table is not the end of the story when it comes to the data representation. All of these tables have relationships to other tables, and it is through these relationships that the full view of the data comes together. So here's the Lego set table we just looked at, and this record is for the Space Shuttle expedition. But these 6 columns don't tell you everything that you need to know about the Space Shuttle. It doesn't tell you what pieces are included, although it does say that there are 1,229. So we need to add another table to represent these Lego pieces. The Lego pieces table has 3 columns, description, category, and ID, and the piece ID in this column is the primary key. But we still need more information to see how those two relate to one another, so we're going to add a third table called set pieces. And set pieces has 2 foreign keys, which relate to the Lego set and the Lego pieces tables. This is a classic representation of a many-to-many relationship in a relational database. And although it's not the only relationship type, this is the general scheme used to represent data with primary keys, foreign keys, and tables. Structured data's properties are a set of tables with relations. It has a fixed schema that does not change from record to record. And SQL is used to query the table for retrieving and manipulating data. This depiction of structured data is pretty much the same across all relational database systems. Semi-structured systems are a lot more diverse, though. And due to this diversity, I can't show you an easy example of semi-structured data like I could with the Lego example. So we're going to start the conversation with properties of semi-structured systems. The phrase semi-structured means many different things depending on the organization you're working at, the technology you're talking about, or the blog post you're reading. But when we at Tableau say semi-structured, we are referring to a format of data which has 4 properties. It has a flexible schema, meaning that the types for any one field can change and they're not enforced. It doesn't prescribe to the relational model like traditional databases do. This doesn't mean that the objects inside of a semi-structured system don't relate to one another. It just means that the mechanisms which enforce those and enable those relationships differ from system to system. And it's not the same primary key, foreign key, many-to-many, many-to-one relationship system that you're used to. Semi-structured data is easily transmittable in reference to serialization overhead. It's a non-trivial task to serialize and deserialize a MySQL database. But JSON files and XML files happen billions of times every day on the web and are even happening right now in the background of all of our devices. Anyone who has forgotten to silence their cell phone in a movie theater has been made painfully aware of this reality. And due to these 3 properties, SQL is not a rich enough language to retrieve or manipulate semi-structured data. To help us wrangle the many different and disjoint systems of semi-structured databases, we at Tableau categorize them into one of 3 main buckets. Passive files is in reference to physical files on a computer. And this can be anything from a few files emailed around the office to full-fledged distributed file management systems with millions of files. The bread and butter of NoSQL databases are NoSQL document stores. NoSQL is a catch-all phrase that different people and organizations use. But by our preference, and just for the sake of this talk, when we're referring to NoSQL, we mean databases that do not use SQL at all to query for their data. A document store database has a lot of analogs to a traditional database. As a traditional database has tables filled with rows, a document store has collections filled with documents. There's also the requirement of a unique ID field for every document, which is analogous to a primary key. This unique ID field can be used and referenced by other documents and queried to get related data. And many of the same simple types that you see in a relational database, strings, ints, floats, dates, and what have you, they're all available in document stores as well. But the analogy breaks down at this point because these document stores hold semi-structured data. So the schema is flexible. The schema is flexible, the data is hierarchical in nature, and documents are a complex object called a label association, which is comprised of other nested label associations, arrays, and simple types. Mina's going to talk about these complex objects in a minute. And the third category of semi-structured systems are hybrid databases. A hybrid database is in reference to a database which is relational in nature but has some semi-structured data. This is typically implemented as a relational table with a column of a semi-structured type, usually XML or JSON. A hybrid database can use generic SQL syntax to query for most of the data in the table, but it requires a custom extension to query the semi-structured column. And this custom extension varies from system to system. These three categories of semi-structured database systems comprise of a really massive set of different databases and architectures. And if we were to try to spend our time discussing all of the different architectures, we wouldn't get very far in this talk. So we're instead going to be focused on the format of the data and not the system that consumes it. To talk about our favorite data format, I'll bring Mina back up here.
Thank you, Stephen. All right, JSON. There are several data formats available for the interchange of data between an application running in a browser client and the server. Now, plain old text files, XML, and JSON are some of the examples. Now, plain old text files are simple, but they lack structure. XML, on the other hand, has structure, but they are cryptic and verbose with a lot of tags. JSON has the best of both worlds. It's both simple and lightweight with no cryptic tags. Now, what exactly is JSON? Now, JSON is JavaScript object notation, which is an open source file format for representing any JavaScript object. Now, JSON was primarily intended to be a subset of JavaScript. And although it is used primarily with JavaScript, almost all programming languages can manipulate JSON data, and so it's language independent. Finally, since JSON is text-based, it is human readable. Now, why is JSON so popular? Simplicity. Now, let's compare this with its arch nemesis, XML. Now, XML is composed of elements, tags, and doc type definitions called DTDs and other meta structures, whereas JSON is composed only of name-value pairs, which are easy to read. And JSON is more flexible. Now, when an object is represented in the JSON format, adding or removing an attribute to it is very easy. Finally, every programming language that you can think of has native support for manipulating JSON data. You can serialize and deserialize natively without the use of off-the-shelf libraries or even having to write parsers from scratch on your own. Now, a quick show of hands. How many of you have worked with JSON data? All right, some of you, but not all. So let's quickly go through the structure of JSON document. Now, JSON is composed of unordered set of name-value pairs. Let's make sense of it with an example. Now, let's stick to the Lego theme that Stephen introduced us to. So here, you will see a description of a corner piece in Lego, and you will see that there are a lot of name-value pairs. ID, description, category, etc. are all names or keys, whereas 2420, plates, etc. are values. And unless you're dealing with a high-level array, a JSON document will almost always be enclosed within curly braces, as depicted here. And name-value pairs in JSON document are delimited by comma, like this here. We have highlighted all the delimiters. And finally, every name or key in a JSON document is a string, and it is followed immediately by a colon, as indicated here. Now, those are the only 4 grammar rules that JSON imposes on you. Now, compare this with XML, which is cryptic. And now let's look at the different data types that JSON supports. JSON supports numbers, strings, booleans, array, objects, and null. Now, null is a little interesting. It basically indicates the absence or non-existence of data in a JSON document. Let's make sense of this with examples. Now, ID here has a numeric value. You will see that it is not enclosed in quotation marks. Now, description is a string. It's a concatenation of characters enclosed within quotation marks. Now here, set is an interesting name-value pair. The value itself is an object, and what I mean by object is nothing but another unordered set of name-value pairs. Boolean value, just like any other programming language, can have true or false values. And finally, an array is a collection of data which can be of simple data types. All right, now we looked at the different data types that JSON supports. Now let's take a look at the different types of name-value pairs a JSON document can contain. We call this simple label association and nested label association. Now, simple label association, like shown in this example, is a flat structure of name-value pairs, as opposed to a nested label association, which contains a hierarchy. Just like I mentioned before, set has a value, which is an object in itself. An object is, again, nothing but an unordered set of name-value pairs. All right. Now, since JSON is very forgiving, and it can usually take anything for names and values, we need to be very careful while designing JSON schema. Otherwise, it can go haywire, and maintenance and analysis can be a nightmare. So we've come up with some best practices to be followed in designing JSON schema. The first and foremost one is that a flatter structure is better. Now, although you can have a really deeply nested JSON structure, flatter is better to understand and maintain. Additionally, you will have this advantage that it will work with most data analysis tools. Now, JSON does not impose too many restrictions when it comes to naming keys, but we recommend that you confine yourself to alphabets and a set of special characters like underscores, ampersands, and dashes. And the third one is to not use correlated arrays. Now, what exactly are correlated arrays? Let's take an example. Now, this is a JSON object with two name-value pairs. You see timestamp and num check-ins are keys, and the values are both arrays. Now, it's not readily understandable what this particular JSON object is conveying. Now, apparently, this is the number of people who checked in today at 8 a.m. and 8:30 a.m. respectively. So the first element in the first array corresponds to the first element in the second array. So they are correlated. This is now understandable after an explanation. However, this can be a nightmare in maintenance. And imagine having to find an error when the array actually grows and to correct it. This can be really a big, huge nightmare. So avoid correlated arrays at any cost. Finally, do not use data associations. Now, what exactly is a data association? Now, we spoke about label associations where we have name-value pairs. We have names and keys, which are strings. Now, here, if you look at the keys themselves contain key data, right? The timestamp itself is used as a key. This is a common practice in most JSON schemas, but we recommend that you don't use it because it's not easily maintainable or understandable. Now again, the intent is the same. It's basically trying to convey the number of attendees who checked in at 8 and 8:30 a.m. respectively. All right, so we looked at ways in which we should not be designing JSON schema. How do we convey the same information in the recommended way? Now this is a recommended way. Now, if you recall, I spoke about a top-level array. Right? Not all JSON documents will be enclosed in curly braces. Here, the JSON document itself is a top-level array with two objects, each having two name-value pairs. So it's clear that it's an array of name-value pairs, and it's trying to convey that this is telling us the number of people checking in at different times. Awesome. So there are some challenges that are inherent in analyzing semi-structured data. Now let's take a look at those. Now Stephen introduced us to all the semi-structured data systems that are commonly used in the wild. Now, they are passive file stores, NoSQL document stores, and hybrid databases. JSON will be under passive file store. NoSQL document stores are MongoDB, Cassandra, CouchDB, et cetera. And hybrid databases, examples for those would be Hive, Postgres, where you have JSON data in one of the columns in a usually rectangular database. Now let's look at challenges that each of these categories poses. Now, passive stores do not have stringent schema rules. So you can actually be very creative and go haywire with the schema, like we just saw. And metadata will always need to be detective. It's not readily available. You need to parse the entire file in order to understand the structure of the JSON document. And finally, there is no formal query language that's available to us in querying passive file stores. Now, let's add some colors to understand the good versus the bad. Well, all are bad in these. All right, now let's look at the challenges in NoSQL document stores. NoSQL document stores do have some schema rules, but metadata would still need to be detected in certain NoSQL document stores. And the query language is usually very different from SQL. And if you know SQL, that knowledge cannot be directly applied on NoSQL document stores. So there's a steep learning curve. Now, finally, let's look at the challenges that hybrid databases pose. Now, schema rules, again, may apply in hybrid databases. Metadata stores may be available where you can directly query the metadata, but every query engine will have its own SQL dialect, and these are actually very different. And so there is a learning curve there as well. All right. So all these challenges have forced us to rethink data analysis when we are dealing with semi-structured data, because data is no longer rectangular. And data no longer has fixed schema because it grows over time. And as we just saw, SQL cannot always be used. Now, to show us the magic of analyzing semi-structured data with Tableau, I'm going to invite Stephen back on stage.
Since you can't wait for the data ecosystem to catch up with semi-structured data in order to get insights out of it, we're all faced with the challenge of trying to fit our fluid and flexible data into our rigid and flat systems. This challenge can feel a lot like trying to fit a square peg into a round hole. The analogy isn't perfect because our rectangular systems would be more like a square hole and our fluid data less like a square peg, maybe more like the star-shaped one. But I'm at the mercy of our common idioms, so we have to make do. The solution to making a square peg fit into a round hole is to flatten and denormalize your semi-structured data so that it resembles the rectangular format that our analysis tools expect. This is a challenging task, and entire economies have been built up to aid companies in this process. And most of the solutions that we've seen are nightmarish combinations of technology smashed together. One of our partners in the development of the JSON connector is Zillow. And Mina and I had the opportunity to go visit Zillow's headquarters in Seattle to learn about their challenges, successes, and frustrations in trying to fit their semi-structured data into their Tableau pipeline. And they've graciously given us permission to share what that flow looks like for them. So Zillow starts with Google Analytics clickstream data in Google BigQuery. From there, it is pulled into a staging bucket in Google Cloud Storage. Hadoop jobs on Google Cloud Platform are run to generate flattened CSV files, which are uploaded into Amazon S3. The CSVs are then loaded into Amazon Redshift, where summary tables are created. And the summary tables are connected to Tableau through our API to create extracts. Finally, data happiness abounds. But we understand that not everyone with semi-structured data is processing at the gigabit scale with a dedicated IT department capable of million-dollar investments to flatten their data for analysis. So for the rest of us, we have the JSON connector. We're going to show you an example of analyzing JSON data in Tableau, and we're going to highlight some of the more common pitfalls you're likely to see when attempting to do so. But we're also going to give you the knowledge and tools to do it like a boss. In Tableau, you can connect to JSON files that are either stored locally or through a network drive that you have permissions to access, or remotely via our Drive and OneNote cloud connectors. And there are two formats of JSON that Tableau will accept, which we call top-level array and single object per line. In top-level array format, the highest object in the hierarchy is an array, and every record is an entry into that array. In single object per line format, although technically invalid JSON, is a format that is consumed and exported from many of the common NoSQL document stores, such as MongoDB. We learn from customer interactions and through the gathering of real-world JSON data that this is one of the most common in the wild. In this format, each record sits on its own line, terminating in a new line character. So Mina is going to drive the demo while I get to boss her around. Payback for the fact that she gets to boss me around every day at work.
Thank you, Stephen. I do have an interesting data. In the interest of sticking to our Lego theme, I have a Lego movies data, which is in the JSON format. So let's
take a look at it.
go ahead. Yeah.
All right, I can see this JSON data is in single object per line format. Lego movie information such as runtime, release, rating, and it looks like we have 29 total records. All right, let's pop it up in Tableau. You can connect to JSON data in Tableau just like any other file connector by clicking on the JSON connector link, selecting the file you want, and clicking Open.
Oh, wow, this is more easy to read.
Yeah, so this is a new UI element that was created for the JSON connector, which we call the schema selector. What Tableau has done to get the data you're looking at is sampled the first 10,000 records of the JSON document. In this case, since there were only 29, this was the whole file, and then inferred the schema from that sample. You can see that we kept the hierarchy of the JSON file visible for you so that you can see the data in its native format. And there are example values for each of the fields to get a better idea of what that field is supposed to represent. Yeah, go ahead and click on that arrow. And there's a little bit of tools here to help navigate. You can hide some of the fields so you can get a better, broader view. And the last thing to point out in the schema selector, those checkboxes on the left side. What it allows you to do is to select only the data that you actually want to use for analysis. So if you have a field that you know it's not going to be useful, you can omit that field, or that level in this case, so that it doesn't clutter up the data set in the end. But for our case, let's select all the schema and click OK.
I see that there are 1,000 rows, but the original file had only 29 objects. What's going on here?
Well, if you expand that, put in 10,000, I bet there's even more.
There's actually 6,936 rows now.
Yeah, so what happened after you clicked OK was, as we said, fitting the square peg into the round hole is to flatten and denormalize the data. So in order to maintain all of the information in the JSON hierarchy, a cross product of each of the fields have to be used. So if there was a single JSON record that had 2 arrays, each of which with 4 records each, it would produce 16 rows in our result set. So all of our arrays and nested objects took 29 records and made almost 7,000 out of it. And this can cause some problems for your analysis, but Tableau has done a lot to help in this process. First thing to point out is the document index field over here on the left side. So you'll notice that it starts at 1, and if you scroll down, it'll increment to 2 and 3, all the way up to 29. What this field tells you is all of the rows. It tells you which JSON record those rows originated from. And there are a lot more fields that Tableau has created to help, but let's go to the sheet view to examine those. So the first thing you might notice up in the Dimensions tab there's already folders created for you. What Tableau has done is put all of the objects that exist inside of each of the levels in their own folder to make it easier for you to find them. You'll also see any of the fields up there that are arrays, there is an index that has been generated. So for every array, we generate an array index. And the reason why will be clear in just a minute. Before we get into that, down in the measures area, there's another folder called source measures. That is where the original measures in the data set reside, and these are dangerous to use because of all of that duplication of rows. So what we recommend instead is to use the generated level of detail expressions Tableau has made for us already. Right-click on one of those, that one, Box Office, and go to Edit, so that we can look at what has happened here. So this is a classic level of detail expression. What it's trying to do is it takes the original measure Box Office, and it sets its level of detail to the document index that Tableau created. And so now whenever you use this, anytime that all of the box office records that would be pulled using the whole result set, it'll just take the maximum of that, they're all going to be the same, and use it just for that document index level. So you don't have to worry about the duplication anymore. The last set of fields that were created are these number of records fields. So there's a number of record calculation created for all of the arrays and levels. And this uses that array index field that we saw previously in another classic level of detail. So it's setting the level of detail of the objects in the array to the document index. So now that we've got an understanding of the data set and what Tableau has done to kind of help us out, what's a question you want answered?
Yeah, I do have a question. Given that Will Arnett is my most favorite actor, or at least most favorite actor who voiced a Lego movie, I want to know who voiced the most number of Lego movies. I hope it's Will Arnett, but let's see.
All right, let's let the data tell us the answer. Take the actor's dimension, put it out onto rows, and let's take the document index field and put it onto columns. Change the aggregation to count distinct. Remove our nulls, there's noise, of course. And sort.
Huh, it was Troy Baker after all. Will Arnett actually acted only in 2 movies. All right.
So now that we're getting into the flow, I have a question. I see that we have a geologic field, country, representing the country that the Lego movies were released in. Knowing that Lego was created in Denmark, it is the land of the Lego, I would assume Denmark has seen most of the releases.
But I think most of these movies were actually made in the US. So I believe it would be the USA which saw most Lego movie releases. But let's let data speak for itself.
All right, so double click that country field to get our map viz started. And let's take the number of records per lego.json and put it onto color. That should be easy to see.
All right. So USA saw 21 Lego movie releases. Canada saw only 1. UK saw 2. And Denmark, my friend, saw only 7.
Looks like the US is the land of the Lego after all.
But wait a minute, even 21 actually sounds wrong, given that we saw 29 objects in the original file. What's going on here?
Well, let's take a look at the JSON file and the raw, see what we're looking at. Do a search for country.
Let's look for country. Okay. That is an array. It's an array. Array again. Array. All right. Oh, there you go. There's a string.
Yeah. So it looks like what's happening here is a classic example of heterogeneous types finding their way into the fluid JSON object, which are legal in JSON, but not handled very well by structured analysis tools like Tableau. Shows the importance of needing to clean up your data some before you get it into Tableau, or you may encounter situations like this. Do you have another question that you want answered?
I do have another question. I want to compare all these Lego movies based on their ratings.
Okay, seeing how which one of them did.
That's right.
Well, that should be easy to do. Under the ratings folder in dimensions, there's a ratings.value. Bring that onto the viz.
These values are in different formats. What's going on?
Bring source out too. Let's take a look. Yeah.
All right. So these values are coming from different sources, and hence the discrepancy.
Yeah, another example of how data is not enforced and can be different from record to record. But some of the cleanup that you need to do to get all of the data to look the same can be done inside Tableau. In this case, I think we can fix this with a calculated field. So right-click on ratings.value and go to Create Calculation.
All right.
And I encourage you to cheat so that we don't have to sit here and type it all out.
I do have a cheat sheet here. I'm going to copy my calcs.
Okay. So this is a bit of a complicated looking calculation, but there's good comments here to help us try to break it down. So we've got those three different formats. One is a percentage out of 100. One of them is a string, which is a fraction out of 100. And one is a string, which is a fraction out of 10. We want to get them all in the same format. And so we're just going to pick a value between 0 and 100 as our resulting format. So to start, we want to see if the field ends in a percent sign. Then we'll know it's from Rotten Tomatoes. And in that case, what we want to do is remove the percent sign and cast it to an int. And that's what that first line does. If it has a slash in the middle of it, which we're doing the contains lookup here, we know it's from either IMDb or Metacritic. In that case, what we want to do is take the value after the slash, that second string, check its length. If it's of length 3, then we know it's from Metacritic, and the first value is already out of 100. So in that case, we just take the first value and cast it to an int, and we're done. Now, if that second number after the slash is only of length 2, then that first number is only out of 10. So cast it to an int, multiply by 10, and now we've got that value out of 100. And if it's in neither of those formats, it's invalid, and we want to return null.
All right.
Bring that field onto the viz.
450K, that doesn't sound right. Do you think there was an error in the calculation?
Well, yeah, the reason why you can tell that that doesn't look very right is there are 29 records. If each of the movies scored 100, there would only be 2,900 total values for the scores here. But keeping in mind that for all of the source measures, Tableau generated a level of detail expression just for this exact problem. And what we did was we converted a dimension to a measure by way of that casting to an int. Anytime that you are going to convert a dimension to a measure, you have to create your own level of detail calculation so that you can avoid this duplication. So let's show them how to do that. Right-clicking on that field we created, go to Create Calc.
I'm going to cheat again.
If you're not cheating, you're not trying. All right, so this looks very similar to the other level of detail expressions you saw, where we're taking this measure and we're fixing it at the document index level. But if you were paying close attention, you would notice that the aggregation on the right side of the level detail expression is an average here, where it was a max before. And this is because movies can have ratings can have more than one rating. They can have ratings from each of the different sources. So instead of just taking the max here, we want to average those 3 to produce the one result, which is the overall rating for that movie. Let's put our new field out on the viz.
This sounds more reasonable.
1600 seems within the range. Change the aggregation to average. Oh, and it looks like the average of all the Lego movies only scored a 60 out of 100, which is not great. But let's see how each one of them did individually, taking title onto columns and sorting.
All right. Looks like the Lego movie was the most appreciated one with 83 average
83 is pretty
rating.
good. 83 is pretty good. But the Master, you said that one was your favorite, right?
That's right, and it has only 60.
Well, don't put too much value in these ratings. They're not going to tell you whether or not you like the movie, just how most of the people who did vote for them liked it.
All right, I think we are running out of time.
Okay. So let's thank you everyone for coming. We're going to take some questions now. But if you're not interested in sticking around for the questions, or if you just need to run for any reason, go ahead and feel free to leave. Everyone else who wants to hear some questions or talk, then go ahead and stick around. Also, if we didn't get to something you were hoping we would, or if you have a question that we can't get to, please feel free to email either or both of us, and we'll make sure that you get the information you're looking for.
Thank you.
For the level of detail calculations that are automatically created
Yeah.
when in a JSON file, have you ever run into any issues of them being incorrect for some reason based on a weird structure in the JSON? Or does it seem to every single time be correct?
Okay, so the question was about the level of detail expressions that Tableau creates for us. Is there ever a situation where they can become incorrect because of some strange structure in the JSON file? And the answer is no. We actually have a bunch of tests in place to make sure that they are being produced correctly, but it's a pretty simple algorithm used to determine how to create those level of detail expressions. So I would trust them as much as you can trust any other field in Tableau. Let's go first.
Any recommendations for dealing with third-party data that's not following best practices? We get reports in that contain the correlated arrays and association.
So yeah, do we have any recommendations for dealing with third-party JSON files which don't prescribe to these best practices that we said?
Yeah, we do not have a very good story for correlated arrays and data associations right now. So the recommendation would be to clean up the data before bringing them into Tableau.
It's a challenging task to programmatically determine what you mean whenever, like, when do you know that the key is actually data in a programmatic way? And so far we don't have a solution to that.
And to add on to that, we actually had a lot of customer interviews, analyzed how JSON data is actually structured in the wild, and then came up with a JSON connector and how LODs are actually generated as well, algorithmically. So it would work in most cases, but in cases where it doesn't, then we recommend cleaning it up before bringing it into Tableau. Yeah.
So in the country, gross client rate, issue the first array, what was the decision factor to say this is an array as opposed to being strings? Some growth strings.
Right. So the country, as we saw, was of different types, right? So we saw that some of those fields were actually arrays and some were strings. So Stephen actually shed some light on the importance of cleanup in that case as well. Whenever there are, JSON doesn't really flag those kind of data where the same attribute is of different types and different objects. And so it's up to us, and during the ETL process, to clean data to make sure that all of these attributes are of the same type and are consistent.
So,
My question is more, why did Tableau decide to use that array rather than string?
That's right. So algorithmically, the design that we went for was to actually go with the first type that we find. Yeah, so the first object was actually an array, and so we assumed that it would be an array throughout.
and
So the
this,
strings.
yeah, this can cause a problem if you know that your schema has changed towards the end of your JSON file, and it's a thing that you need to just keep in mind.
Yeah. Yes.
Does Tableau have a,
Sorry. Please.
a partner that will help convert data to a JSON file?
Data to a JSON file. You mean data which is in different
Yeah,
format.
Something that is
We will have to.
into a JSON.
We'll have to research on that topic, and we can get back to you if you can share your email ID.
Oh, sure.
Yeah.
So did you guys do any benchmarks against MongoDB and other JSON databases? I think this uses your Tableau database engine to index the JSON and Postgres, I believe. So did you compare against MongoDB's natural JSON?
We did some early on, but MongoDB actually, oh, sorry, of course. He asked if we did any benchmarks to compare the performance of our JSON connector to connectors native to other NoSQL databases like MongoDB, for instance. And we did some early on. I don't recall I remember if it were really bad, we wouldn't have been able to continue. And so we got it to a consumable amount. But this isn't necessarily a competitive connector to the MongoDB BI connector because it's dealing with a smaller amount of data not housed inside of a database.
And this is hyper-enabled, right?
Yes.
Yes. Yeah, not right now.
So hold on, Mina, the repeat of the question.
Yeah, sorry.
He asked about whether or not Tableau will recognize a semi-structured column inside of a hybrid database whenever we connect to it natively.
Yeah, so the recommendation today is to write custom SQL. Once you actually connect to these kind of databases, which would have JSON as one of their columns, then write custom SQL to flatten what JSON connector does behind the scenes for you. But in which case you will actually have to write these level of detail calculations yourselves. But we do not support that as yet in Tableau.
Yeah.
Yeah.
Can Tableau connect to REST services given a URL that output in JSON yet?
Can Tableau connect to REST services given a URL?
We do have web data connectors, and I believe there's a talk later today about web data connectors. So you should go attend the talk and learn more about that. But we do have web data connectors.
Yeah, and as we mentioned, the other cloud connectors that we support to have the same native JSON support that local files do as well.
Thank you.
I was originally using the JSON connector for REST API for ServiceNow. It was great to see that now in 10.3 you can connect that natively. I'm just curious if there's any other like popular tools if you were allowed and part of that based on JSON and how that process worked.
So, can you repeat that question again?
Sure, I was able to use the REST API to pull data from ServiceNow and JSON, parse it from the need, and then you come out with a native connector to ServiceNow in version 10.3. I was just wondering if the JSON team was part of that behind the scenes, if there's any other type of popular service management tools that you're thinking of in the future that are the same too.
Yeah. JSON connector was not actually part of that, but we are actually trying to, broaden the support that we have for other connectors as well, and announcements about that will continue.
Yeah, we
have to
can't
wait, yeah.
give away any of our secrets of what's coming out or whatnot, but thank you for using it. Any other questions? Yeah.
A minor question. What was that cool editor that you used to highlight the structure?
VS Code.
VS Code?
Yeah.
Is that what's good for popping out and seeing errors in the original JSON?
Yes. We use VS Code for development as well at Tableau. So that's something. It's an open source editor. You should give it a try.
Yeah, sounds good.
Just a little note on that. Mina did work for Visual Studio,
Yeah,
so she's very
back at
gung-ho about it. Just thought we should play that out there. But yes, we all do use it.
And when you're correcting your source JSON files, I mean, when it's a mess, strategies, like do you use Perl scripts to parse it out and rewrite it?
So yeah, what are some of the strategies we might use to clean up and deal with the JSON files? Myself personally, and I've had to do a lot to generate various test files for the sake of creating the connector, is to use Python.
Yeah,
But
Python is
whatever
pretty
language
tough
you're
to
most
use.
comfortable with, they all have a JSON native parser that you can just load a JSON file. It'll convert it to the objects in the language, and then you can manipulate it and then just print out a new JSON. So it's really easy.
Any other questions?
All right.
We will get access to the slide decks, right?
Yes.
I will just email you from that.
Yes.
Thank
Yeah.
you.
Thank you so much.
Thank you, everybody.
Thank you, everyone.